Hi, my name is Harlan. Welcome to the H. Machacon Mechanical Engineering channel. Last week, we discussed in our video tutorial the analysis of an existing heat transfer fluid system in a manufacturing facility, and that was part one, which covers the primary pumping circuit. And today, we will discuss the continuation, part two of the analysis of an existing heat transfer fluid system, and this covers the secondary pumping circuit. For the secondary pumping circuit, there are four users, and these are all reactors connected in a direct return configuration. And there are four secondary pumps, one for each reactor, and each of these pumps is rated at 220 US gallons per minute at a head of 125 feet. Heat transfer fluid, fresh from the primary circuit, is used to kickstart an exothermic reaction during the heating mode. And during the cooling mode, a portion of the heat transfer fluid leaving the reactor is cooled by the water coming from the cooling tower, and this cooled oil is mixed with heat transfer fluid direct from the primary circuit and then pumped back to the reactor in order to maintain the desired temperature. Let us examine closely the pumping circuit during the heating mode in the piping and instrumentation diagram. Here on the left side of this match line, we have here the supply line coming from the primary circuit, and here we have the return line going back into your uh, oil heater. And for each user, we have a reactor and one secondary pump for each reactor. We also have one heat exchanger. During the heating mode, heat transfer fluid coming from the supply line is led into the suction of the secondary pump and then into the bottom coils of the reactor to start in order to kickstart a reaction. That will be the heating mode. And once we have a reaction being started, and it is exothermic, so we need to maintain the temperature. Yeah. So how is it being done? So the cooled oil here is cooled further on the heat exchanger with water coming from the cooling tower to reduce its temperature. And this cold fluid is mixed with the fresh heat transfer fluid led into the suction line. And the amount or the ratio of the mixtures, cold and hot, being controlled by this valve in here. So, what is the problem? The four reactors are not able to operate simultaneously because of insufficient heat supplied by the primary line. Let us show to you the uh, primary line here. And so if these four reactors operate simultaneously during the heating mode, what happens is only these two reactors are being supplied, and these 3 and 4 will have insufficient heating. So how are we going to approach the problem? First is we calculate the system head of the pipe and components involved in the heating mode. and compare it with the rated head of the secondary pump. We are concerned only with the heating mode because that is where the problem is. And then once we determine the head, we evaluate the optimum flow required to kickstart an exothermic reaction. So let us proceed to the calculations for the required pump head and secondary pumping circuit. Total head. Total head will be equal to the pressure head plus elevation head plus the head loss. So for pressure head, we solve the pressure head for a given operating pressure of 15 pounds per square inch and a density of CalFlow AFP transfer oil at a temperature of 260 degrees Celsius to be equal to 44.7 pounds per cubic feet. So pressure head will be equal to 15 pounds per square inch times 144 square inch per square feet all over 44.7 pounds per cubic feet, and the result will be 48.32 feet pressure head. For the elevation head, we have 11.6 feet as measured. Let us go now to head losses. For reactor number 1, secondary circuit on the heating mode, it consists of valves, pipes, and fittings that are basically 3-inch in size, plus the reactor bottom coils. Let us first consider the head loss in the 3-inch pipes and fittings. So from the piping system's manual, the design value of the absolute roughness for a steel pipe is 0.0002 feet. And the relative roughness of the 3-inch steel pipe will be equal to the absolute roughness of 0.0002 feet divided by the diameter of the 3-inch steel pipe, which is 0.256 feet, and the relative roughness will be 0.00078. Then we solve for the dynamic viscosity of the dynamic viscosity of the CalFlow AF heat transfer oil has been solved already. So no need to solve already in the previous tutorial. To be 0.000336. Then we calculate the velocity of the fluid in the 3-inch steel pipe at a given flow of 220 US gallons per minute, and the velocity here will be equal to 9.52 feet per second. And calculate the Reynolds number from the piping systems manual. Reynolds number will be equal to the density times the velocity of fluid times the diameter in feet divided by the dynamic viscosity. You will have the result here will be 323,646. So looking at the Moody diagram, and we have the value of the relative roughness, and then we also have the value of the Reynolds number. So the relative roughness will be 0.00078, and then the Reynolds number 323,646 here. So it's at this level here. Reynolds number will locate 0.02. And from the piping systems manual, we tabulate the friction components and determine the equivalent length of the setup. So these are the components, 3-inch components, and the quantities of each. And then we have here your unit equivalent length and the total equivalent length here be 484.9 feet. And solving for the head loss, the 3-inch pipes and fittings using the Darcy-Weisbach equation. Head loss, the Moody friction factor 0.02, equivalent length of 484.9. The velocity is 9.52. You square this, and then you 2 times the diameter 0.256, and the acceleration due to gravity 32.2 feet per second squared, and the head loss is equal to 53.31 feet. Let's now consider the head loss in the 2-inch half tubes, the bottom of the reactor. The pressure drop across these bottom coils of the reactor was measured to be delta P 7.5 pounds per square inch. And solving for the head loss will be the pressure drop times 144 square inch per square foot all over the density, 44.7 pounds per cubic foot. The result will be 24.16. So we tabulate the values. We have pressure head 48.32 and the elevation head 11.6, and the head loss for the 3-inch pipes and fittings 53.31, and for the 2-inch shaft tube coils 24.16. The total required head during the heating mode is 137.4. And you will take note that the total head loss for the secondary pumping circuit during the heating mode, so for the head loss alone, is 53.31 plus 24.16, which totals 77.47 feet. Our calculations show that the total head requirement for reactor number 1 during the secondary pumping stage on the heating mode is 138.8 feet. The secondary pump for reactor number 1 is rated at 220 gallons per minute at a head of 125 feet, and the resulting flow would be in the vicinity of 190 gallons per minute. So a secondary pump flow of 190 US gallons per minute during the heating mode will tend to starve the rest of the reactors. The starvation problem becomes aggravated in reactors 3 and 4, which are located at the end of the heat transfer oil supply line. The primary circulating pump, as calculated and measured during our previous video tutorial, feeds only a scanty of 260 US gallons per minute to the 6-inch heat transfer oil supply line. This leaves only 70 US gallons per minute for the rest of reactors every time reactor 1 is on heating mode. And to address this issue, the secondary pumps, all of them, should have their flows reduced through variable frequency drive. If we divide the flow of 260 US gallons per minute from the primary circulating pump equally among the 4 reactors, 65 US gallons per minute will be available for each reactor. The question is, will 65 US gallons per minute be sufficient to kickstart the chemical reaction? Answer is yes. if the flow is turbulent. So we can verify it using the flow patterns described in the piping systems manual. That for laminar flow, the Reynolds number is less than 2,300, and during transitional flow, it is in a range between 2,300 to 4,000, and for turbulent flow, it is above 4,000 Reynolds number. So let us check whether the flow is turbulent if we set it at 65 US gallons per minute. So for 65 US gallons per minute at a diameter of 3 inch, so we do the calculations, the velocity will be 2.81 feet per second. And we calculate the Reynolds number, the density 44.7 pounds per cubic feet, velocity will be 2.81 feet per second, the diameter is 0.256, and the dynamic viscosity is 0.0000366, and the resulting Reynolds number is 95,530, which is greater than 4,000, meaning the flow is turbulent. And the solution: so install a variable frequency drive on the secondary pump motors to reduce the flow from 220 US gallons per minute to 65 US gallons per minute. And how are we going to quantify whether the flow is already at 65 US gallons per minute? We measure it using an ultrasonic flow meter. And we are very uh, uh, advantageous because of our partnership with FRS, Instrumentations and Control Incorporated, who introduced us to their very modern measuring equipment. And one of it is the uh, high temperature ultrasonic flow meter, which we use to measure the flow. So we can quantify it 65 US gallons per minute. Thank you for watching, and we'd like to invite you to our next video tutorial and subscribe to our YouTube channel, H. Manchutan Mechanical Engineering channel on YouTube. Thank you. Bye now.